what we're going to work with is the law of sines. We're now going to break the chains that have held us to right triangles, and we're going to look at all these other triangles, because right triangles are just one narrow category. All other triangles that are not right triangles can also be solved. It's just that we need different tools to do it. So what we want to do today is two things. First of all, you have to decide if you have enough information. Okay, so the first thing we're going to do is if you're shown a triangle or some angle side information, you got to decide if it even forms a triangle or if it's even possible to solve it if you have enough of information. That's the first thing we're going to do. After that, we'll use the law of sines. There's two main tools for solving non-right triangles, the law of sines and the law of cosines. We're going to work with the law of cosines on Monday. Today we're going to work with the law of sines. Now there's a right and a wrong time to do that, and so we're going to recognize when the appropriate time to apply the law of sines is. Now, a little information about triangles that aren't right triangles. First of all, any triangles that don't have a right angle are oblique. End of story. Now, when we're working with oblique triangles, the trig ratios sine, cosine, tangent don't apply. They only work on right triangles, so we can throw those out. You can't label sides. You can't have a hypotenuse if it's not a right triangle. You can't have an adjacent side if it's not a right triangle. We still use opposite in some sense, but we really can't use the same labeling system that we've used before. Now think about this for a minute. If my goal was to give each of you a ruler and a pencil, we won't do this because it takes too much time and it's the benefit is easily understood anyway, but if my goal was to have each one of you draw the exact same triangle on your paper, how much information would I have to give you to do that? Obviously, if I gave you all three angle values and all three sides values, you'd all end up with the same triangle. But can I get by giving you less than that? The question is, what's the minimal amount of information that you need in order to make sure that everybody's triangles would be the same? Well, here's the key. Every triangle's got 6 parts, right? 3 sides, 3 angles. In general, you have to know at least 3. If you don't know at least 3, there's no way that you can define a triangle. For example, if I said I want each one of you to draw a triangle with a 45-degree angle in it and a side length of 7.2 meters, well, you could all do that, but you would not necessarily end up with the same triangle. There's hundreds of different triangles that would meet this criteria. Or if I said I want all of you to draw a triangle with an angle of 52 degrees and a 68-degree angle, you could all do that. Your third angle would be the same, but they'd all be different sizes. So 2 pieces of information isn't enough. Now, if I tell you that I want your triangle to have a 52-degree angle, a 68-degree angle, and a 2.5 centimeter side, they're all going to look exactly the same. Because 3 pieces of information will define a triangle, and we're going to see why that's true. That leaves us with 6 possible things that can happen. There's 6 different ways you can be given 3 pieces of information. First one is you can be given all 3 sides. Okay? If you're given all 3 sides, there's no doubt about it, that will define one triangle. If I told everybody that I want you to make a triangle with side lengths of 3, 4, and 5 inches, they would all look exactly the same. No doubt about it. There's no room for variation. Another way that you could do this is if you were given what we call the SAS case, side angle side. And that's if I told you 2 sides and the angle in between them. Now, if you think about that, let's say that we had a triangle here. I told you that this was 5.7 feet. This side was 4.6 feet. And this angle was 17 degrees. Don't you agree that since we know this side, this angle, and this side, side angle, side, this side just has to basically connect the ends. There's really no variation in how that triangle can be formed. So that's another case where the triangle would be defined. Notice that the A is between the two S's, which means your angle is between the two sides. The third case that we could be given is side-side angle. So if we're given two sides in an angle, we're given two sides where the angle is not in between. For example, there's a case where I've given you two sides, I've given you one angle, but the angle is not between the two sides. That would be the SSAA case. And we have to handle that differently than the side angle side case. Well, angle side angle. You could be given two angles and a side where the side is between the two angles. Something like that. If you know one side length and the angles on each end of that side, there's only one possible triangle, because those two sides are going to leave this known value at these angles. They're going to come up and they're going to meet out here. There's no question about that. We'll be able to find all the other values. Well, what two cases haven't we considered yet? There's two more scenarios. Could be given all three angles, or two angles and a side, but the side is not in between. So if you're given two sides in an angle, the angle could be between or not between. Or in the last two, if you're given two angles and a side, either the side is between or it might not be between. There again, if we're given that information, that would define a triangle. There's no question about what the triangle has to look like. All the other information will be able to be found. Now the last case is kind of unique. Notice there's 5 cases there, and those are the 5 cases that we're going to be working with over the next 2 days. Notice that the last case that Bill mentioned, all 3 angles, that's not enough to define a triangle. You always have to have at least one side to give the triangle scale. There's 2 triangles. They share common angles, angle, 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 but those 2 triangles are not the same. So being given 3 angles is not enough to define the triangle. If we wanted to find the side length, there's no way we can do that. Okay, so we always have to have at least one side to define the size of the triangle. All right. Now the next fact will shock and amaze you. Questions about that, or does it look okay? Now, the next thing that we're going to see, we're not going to prove why it's true. We're just going to observe that it is true. I missed a slide. Just a thing to note here, the next slide will shock and amaze you. We're going to see, today we're going to focus on 3 cases. Today we want to look at angle, angle, side angle, and side, side angle. We'll look at the 2 other cases that we can solve on Monday. Now, I'm going to put a triangle on the screen. We just noted that. Given 3 angles, we can't solve the triangle. We'll see that some more a little later. Okay, there's a triangle. I'm going to draw that a little bit bigger so that you can see it. Okay, here's what I'd like you to do. What we want to do is we want to compute 3 ratios. We want to take each side length and divide it by the sine of the opposite angle. Okay, so here's what I'm going to have you do. You 3 guys in the front row, I'm going to have you take the side length A, 12, and divide it by the sine of angle A, 106.07. Second row, I'm going to have you do the same thing for B. Take side B, 7, and divide it by the sine of angle B, 34.07. Everybody in back here, C. Side C, divide it by angle, by the sine of angle C. If you do that, you're going to have, for A, you'll have 12.00. 12 front row, what'd you get for side A divided by sine of angle A? We'll go to 2 decimal places here, 4 sig digs. You get 12.49. What'd you get? 49? 49? Okay, second row, 12.49. I'll wait for you to catch your breath here. And everybody else, 12.49. As it turns out, the full proof of why that works is in your text. We won't take the time to do that. But the important thing is that the sine of any angle is always going to have the same ratio to the opposite side, regardless of which angle you're talking about. Now, what that means is, as long as you know any side length opposite some angle, you can determine what that ratio is, and then you can find all the other ones. So anytime we've got a case where we know an angle and an opposite side, we can use that fact to find the rest of the parts of the triangle. That is called the law of sines. Now, you can use the law of sines either way. The way that we set it up, we took the side length and divided it by the sine of the angle, the opposite angle. You could, of course, flip that over and the same thing is true, and either one of them works just fine. Now, that's in your book, but that fact is really what we're going to be using for the rest of the day here. But that will only work if what's true? What do you have to have known about this information in order to be true? It'll work for any triangle as long as you're given one particular the information in a particular way. What one thing has to be true to know any one of these ratios? You need to know the sine of an angle and the opposite side, okay? Or a side and the opposite angle. If you don't know any opposite pairs, then we can't establish that ratio and it's useless. Well, what that means is we can use it anytime that we have one of those 3 cases: angle, angle, side, angle, and side, side, angle. The other 2 cases that we can solve, side, 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 obviously side, 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 we can't use it because we don't know any angles. And side, angle, side, we won't know it because we won't know the side opposite the angle. We'll look at those Monday. Now, that's the law. We're going to do some examples now and see how you use it to fill in unknown values of triangles. But questions about the rule? Now, first of all, what case are we given? We're given ASA, angle, side, angle. So the first thing you have to check when you're given a triangle is what scenario am I given? And is it one of the ones where I can use law of sines? Okay, well, what's the one thing that has to be true? What do you always got to look for before you can use law of sines? You got to know a side and an opposite angle. Is that the case here? Not immediately, but we know this side, so we would need to know this angle. Do we know that angle? We do. As long as we know 2 of the 3 angles in a triangle, we can subtract to find the third one. So technically, we're not given the third angle here, the angle we need, but we can find it real easily. So we can do that. This angle will be 180 minus 117.2 minus 32.7. Turns out to be 30.1 degrees. Now let's label these vertices so that we have some good names here. Let's call, this is arbitrary, but we'd call the top one left A, B, and C, just so we can refer to these easily. Okay, now we need to find, we now know 4 parts. We were given 3, we were given 2 angles and a side. By subtraction we found the third angle, so now we've only got 2 sides to go. We can find either one next. Let's go ahead and find side B. We find one at a time. Now, we set up our proportion. We can use this either way. But we'll do one each way in this problem. We can say that the sine of 30.1, let's do this down here. Sine of 30.1 degrees over the opposite side, which is 250, that has to be equal to sine of an angle over the opposite. Let's use a sine of 117.2 over b is what we want to find. Everybody agree with that setup? Sine of an angle over opposite side has to be same proportion. They got to be equal. Now we just cross multiply. In this direction we get 250.0 times the sine of 117.2 degrees. That's equal to b times the sine of 30.1. Well, then you're home free. You just need to divide both sides by sine of 30.1. That cancels. And now b will be equal to 250 times sine of 117.2 divided by the sine of 30.1. A little calculator work there. Anybody crank that out already? 443.4 is right. .4, and we have another side. All right, well then we can go ahead and find C. Now again, kind of like with right triangles, you like to use information given as opposed to information you've calculated, because any rounding error or mathematical error in your calculation is going to roll into your next result. So we can say, we're still going to use this one because those were given. The sine of 30.1 over 250 is going to be equal to the sine of 32.7 over C. Agree with that setup to find side C? Okay. Well, again, cross multiply. We won't go through this every step, but first couple here we will. 250 times the sine of 32.7 is equal to C times the sine of 30.1 degrees. Divide both sides by 30.1. And you'll have side C. And it turns out to be? That's right. We're done. We solved it. We now know all the angles, all the sides, nothing left to do. Good. That was angle, side, angle. Let's do one more. There's one little problem that arises with the law of sines. That's what we need to spend a little bit more time on. But before we look at the little problem that we're going to come up with, let's just do another real basic case. Wouldn't be a complete day if we didn't do something with radians. So suppose we have that triangle. Now, what case have you got here?
Angle, angle, side.
Angle, angle, side. Two angles in the side is not in between. Well, it's angle, angle, side. It meets our criteria of having an angle and an opposite side known. In this case, it's angle B and side B. But let's do the easy part first. Let's find angle A. How do you find angle A? We're in radians.
500.
Yep. take pi and subtract these two. Just like all the angles in a triangle have to add up to 180 degrees, all three angles have to add up to pi, which is the radian equivalent. So if you take 3.14 minus 0.847 minus 1.251, you'll get that's right, 1.044 radians. Okay, 1.044 radians. Okay, well now we can use law of sines. Let's find side A. Now this time let's use the law of sines upside down. We didn't have to, but let's just flip it over and put the side length on top. So we have A over the sine of 1.044 radians is equal to, now here's the ones that we knew, that's the matching pair that we have, so 2.650 sine of 0.847. All right, well now we can cross multiply. If you do that, you're going to get A equals 3.057. Now we know two sides. We already worked out the third angle. There's only one more thing to go here, and that is side C. So we know that C over sine of 1.251 radians. Remember, if you're in radians, you technically don't need any units on there. I usually put the R to clarify, but when you're writing, as long as you don't put degrees, it's assumed to be radians. Just keep that in mind. So C over sine of 1.251, that's side length over sine of opposite angle. Go back and use the one that we knew. That's 2.650 over sine of 0.847. And if you solve that one, 3.357. And we know both sides. We know all three sides. That triangle is solved. We got all the sides and all the angles. Again, we had to have three pieces of information to start with. If we had less than that, can't do it. Make a note of this. This is described in your book. Don't try and make sense of this. I just want you to make an observation. Those two triangles both have the same side-side information given. If I tell you that I wanted you to draw a triangle with side lengths of 2.35, 4.25, and an 18-degree angle not in between, those are the two things that you could come up with, and they would both be correct. So when you're given two sides and an angle that's not in between, there could be two solutions. There could be two different answers. The two that we've done so far, angle, side, angle, and angle, angle, side, there's no danger of that. There's only one combination. But when you come up with side, side, now picture how that could be. There's our 4.25 side. I'm going to put an 18-degree angle or so on here. It's going to go for quite a ways. That side can be any length because we're not given what it is. Now that means that I can take that other side that's given, 2.35, and it can either fold inward and be 2.35. That forms a triangle that meets the criteria. Or it can fold outward. And that would form another triangle. So there's two possibilities. So when we're given side-side angle, we got to look at both possible triangles that could be formed. And there's a little test. First of all, don't you agree that this 2.35 could be a little bit shorter and it would still form two triangles? You agree with that? If I were to shorten this up, I could still form two triangles. They'd just be a little bit closer together. Or they could be shorter yet, but sooner or later you hit a minimum length where that opposite side can't be any shorter. And what kind of a triangle would you have when this side gets shorter and shorter and shorter as it could fold in or out? Sooner or later, you get to a point where it just barely even reaches. Then it can't fold in or out because it'll be too far away. It just barely reaches that opposite side, and that's the end of it. So when you hit that minimum length, you've only got one kind of a triangle there. What kind of triangle do you end up with? You end up with a right triangle. If it just barely makes contact, you end up with a right triangle. We call that minimum length H. Because the first thing we have to do when we're given information is we have to decide, is that side even long enough to form a triangle? Well, here's what to do. And there's a lot of information on these next two slides. These are on your paper. Okay? Whenever you see a side-side scenario come up, you have to first decide whether or not you can make a triangle. And you do that by noting whether the angle you're given is acute or obtuse. Now, we've been looking at an acute angle, 18 degrees here. But let's say it's obtuse. So I'm going to draw some triangle where I know this side, and I'm going to say that my angle here is obtuse. Now we're going to be given this side will be known, this will be known. What's the shortest this side can possibly be to still form a triangle? If it's too short, it just won't reach over here. Okay? So how long does this red side have to be in order to form any triangle? There's one possibility. It could be longer, could come up here, could be longer yet, could go up there, could be a little bit shorter and go down here, could be a little shorter yet. But what's the shortest that this opposite side from our angle can be before it won't even form a triangle anymore? Got to be longer than the known side. Exactly. If it's shorter than the known side, or what we call the included side, the one in between, it won't even reach back here. Can't form a triangle. So if the known angle is obtuse, the opposite side, the red one in the picture, has to be longer than the known side. If it's not, no triangle possible. If it is longer, then you can form a triangle, and it will be an obtuse triangle. If it is longer than this, then somewhere it's going to go up here. It's going to meet up with this other unknown side. This would be our angle theta that we know. That's our opposite. We still have the angle side-side case. It'll meet up with this side. Triangle lives happily ever after. It's no problem. So that's the test you need to run if it's obtuse. We'll do some examples of these in a minute to help clarify it. But that angle could be acute. And that's the case we were working with a minute ago. If it's acute, we have to decide what H is. So now we know our angle theta. We know one side next to it. We call it included because it's between one that we know and our known angle. And the shortest this can be is if it comes up and forms a 90-degree angle. And we call that value H. H is your minimum length to even form a triangle. Now, what has to be true? We know this angle theta. We know the opposite side is H, our minimum length. And we know that this side would be known. Again, this is for the shortest possible side. And then the sine of theta is what over what? Opposite, which is H, over the hypotenuse, which is your known side. Or in other words, we call it the included one. That one's the opposite one. This is the one in between. It's included between the two. So we just found a formula to check what the minimum length is. Multiply both sides by included, and H is equal to sine of our known angle times the included side. So if we have the side-side angle case, the first thing you need to check if it's an acute angle that we know, can we form an angle? We'll see an example of that in a minute, but we'll finish out the scenarios here. If the opposite side over here is shorter than H, you are out of luck. That's right. You can't form a triangle. So if your opposite side is shorter than what you will calculate to be h, no triangle, pencil down, we're done. However, if it's longer than h, we have a triangle. And if it's longer, it can either fold out or it can fold in, and those are your two scenarios. But if it folds in, what's the longest it can be to still fit in here? It has to be shorter in the known side. So if we get an opposite side that's longer than h and longer than the known side, it can't fold in, it has to fold out. And that's our one triangle. Now the last case that could happen is that it's longer than h but shorter than known, and then it can fold out or in. And we've exhausted every possibility. So if the opposite side is longer than h, that is, it meets the minimum, but it's still shorter than the known side, so it can fold in, it can fold out or in, and we'll have our two possibilities. And that's what we saw on the first screen. So now we're going to look at some examples. We're going to start from scratch, determine whether or not we can form a triangle, and if so, what they look like. Now for the next examples, I don't have any pictures because we don't know what they look like. So we're just going to be given this information. Okay, we're told that we have a 28-degree angle, and the opposite side from that, if angle A is 28 degrees, then side A is 3.47, and the other side that we know is 8.25. So here's what to do. You make yourself a sketch. And always make the sketch the same. Here's what I was shown to do at one point, and I still do it because it seems to make the most sense to me. You start out with a side that we know, and we put our angle down here. It's 28 degrees, so it might look something like this. Now, our opposite side over there is going to be side A. That's angle A. So side A way over there is going to be 3.47. Now we can't complete it yet because we don't know if it's long enough. Now the side that we know, we just put on the bottom. So we're going to make this side B. That's 8.25. And now based on the fact that you put your known side on the bottom, for this case, what is the letter of the vertex down here got to be? C. That's right. It's got to be C. Angle A is here, side A is there. This is, according to what we were given, we always put the known one on the bottom. So this is side B, which means angle B has to be on the top, and that leaves angle C down here. So the question is that 3.47 long enough to reach up, hit that other side, and form a triangle? How do you find out? You got to solve for h. H is equal to the sine of our angle times the included side length, 8.25. So if you take sine of 28 times the included length of 8.25, and you find out that h, our minimum possible length, even to have a triangle, is 3.87. Okay, so opposite side length's got to be at least 3.87 even to reach. Do we have a triangle? We don't. Problem's done. Now, different information, different letters, but we're going to set it up the same way. This time, we're given angle C, so we'll put that down in the bottom right. We're told that that's 38.5 degrees. We're told the opposite side length here is 205. We don't know if that's long enough yet or not. We're told that the other side, B in this case, has to be 253. Now, are you clear on why the 205 and the 253 go where they do and not switched around? 205 is opposite the 38.5. That's why it has to go over there. All right, well, the first thing we need to do is check and see if we can even form a triangle. H equals sine of 38.5 degrees times which? 253. And so our minimum side length is what'd you get, Bill? Yeah, about 157. All that matters to us is that our opposite side is in fact longer than that, so we've got a triangle. Okay, now the question is, can it fold out and in, or can it just fold out? So we do have triangles. Now we need to compare that to this side. We know it can always fold out. Because it's longer than 157, we can fold it outward to form a triangle. Would the 205 fit to fold in? Yes. It does, because it has to be shorter than 253. So our 205 can fold out, or it can fold in. There's our two possible triangles. The opposite is less than the included. So we can fold out, and since it is shorter, it will fit to fold in. We have two possible triangles. Now that we figured out we've got two, we can find out what they are. What if our opposite side would have been 270? If the opposite side was 270, it's still long enough to form a triangle, but would it fit to fold in here? And so it could only fold out. We'd only have one possible triangle. Okay? So we know that we've got two. We can now go ahead and solve them. And solving them is slink. Once you figure out that you've got two, it's not difficult to solve both of them. So we got most of the work done just by figuring out how many possibilities there are. Look okay? All right. Now, as long as we know we've got two, we draw both of them. I got to erase this for a minute, but one of them's going to fold out, the other one's going to fold in. So in either case, we've still got our 38.5 degrees here. We've still got a bottom side of 253. This one will fold out and be 205. This one, still 253, still 38.5 degrees, but it's going to fold in. Agree? All right. Now, you're going to get a kick out of this. You use law of sines to solve them both at the same time. The bottom right one we said was C. The bottom left one has to be A. The bottom left one has to be A because 253 is side B, which means the top one has got to be angle B. And this one is side A. Okay? So, we use law of sines to find B first. We know that the sine of 38.5 over 205 in either case right? Because either triangle, we know the 38.5 on the opposite side. In either case, that's equal to the sine of B, wouldn't matter which one we were talking about, we'd say the same thing, over 253. Agree with that? That's true no matter which one we were talking about. Whether we were talking about the left or whether we were talking about the right, we'd write the exact same thing to solve for sine b. Okay, well, another approach to cross multiplying is to just say we want to multiply both sides by 253 and get the same thing as if we were to cross multiply. And so sine of b is equal to 253 times the sine of 38.5, 0.768. That's right. So if you work that out, you get 0.768. Now take the inverse sine of both sides, and b equals inverse sine of 0.768. And what does your calculator tell you? Remember, now this is a case where there's always two solutions to this, but your calculator only tells you one. This says that the angle is 50.2 degrees. So it told us the angle for which one of those, just by inspection. The left or the right? It's got to be the left one. This one's obtuse. More than 90 degrees. This one up here is 50.2 degrees. This one down here in the bottom, or this one, is the other solution to this. Remember, when we solve this, this is your last quiz right here. Find two solutions to that statement. When you take an inverse sine, there's going to be two solutions. It's positive, so which quadrants are you going to be in? Sine is positive here, which we just found. All and over there's the other one. So we know that it's 50.2 degrees, and 180 minus 50.2 tells you that the other solution is 129.8 degrees. That's the other one. 129.8 degrees. Okay, the math doesn't lie. There's two possible triangles, and when we solve this equation, it tells us there's two possible angles for B. Now, we don't have time to finish these out, but at this point, you're home free. You've got to solve them both, but can you find the third angle for each of these? Sure you can. For the top left one, take 180 minus 50.2 minus 38.5, and we get, what do we get? We get 91.3 degrees. And now we can use law of sines to find that missing side. If you do that, it works out to be 329. This one, 180 minus 129.8 minus 38.5, leaves in this corner 11.7 degrees. Now we know all three angles and two sides. We can use law of sines to find this third side, which works out to be 67. We solved them both.